Good evening, one and all. I am doing a continuation on number 6 for the midterm revisions. So essentially what number 6 was a B model, which was given to us as dB over dt, which is equal to 0.08b minus 1.1t. Essentially what this is asking, or telling us really, is the amount of B's within the rate of change of B's with the respect to the rate of change in time. So A is actually asking us, saying, okay, we'll use the method of integrating factors to solve this differential equation. So I started off initially when I did the midterm, I just said that variables, which pretty much thing else for you, which is why you pretty much got it wrong. Now that I know exactly what to do now is the fact that you use integrating factors. So I have it set up right over here as our normal equation as dB over dt is equal to 0.08b minus 1.1t. So now we got to actually just have our equation to set it up in the proper format, which is what looks to be similar as y equals mx plus b, which is our change in y with respect to time is equal to a of t times y plus b of t. From here, we have to find our mu, our integrating factor, basically. So we have our mu of t, which is equal to e raised to the negative integral of a of t dt. So as I know that I just have my a of t right over here as 0.08 times v, which is our y. So I have this right over here as our mu of t is equal to e to the negative integral of 0.08 dt. And essentially, once you do the integral, which is just negative 0.08t, you have the complete u of t as an e negative 0.08t. And now that we have that, we essentially want to have our, now we have our mu of t, we want to set it up to the rest of the integrating factor, which is our essential solution, which is y of t, which is equal to 1 over mu of t times the integral of mu t times bt dt. Whew, that was a mouthful. Let's try saying that 10 times fast. So now that we have that, we start plug and playing. We have y of t is equal to 1 over e to the negative 0.08t times the integral of e negative 0.08t times 1 of t, excuse me, 1.1t dt. Now, what's interesting is the fact is that when I started doing this, it looked kind of funky. I'm like, well, this is simply, this is probably going to be separate, how do I call it? I'm going to have to integrate this by parts. So by integrating by parts, I decided to actually put a little small section of the math right over here. So as we scroll down, we can see here the negative the integral of e to the negative 0.08t times 1.1t dt. Since 1.1t is just strictly, well, at least 1.1 is just a constant, I just factored that sucker out. So I have 1.1 integral of e negative 0.08t times t times dt. So then, now, following by integrating by parts, I essentially set my u of t, my u is equal to t, and my dv is equal to e to the negative 0.08t. This does help out a lot because the fact is, for one, I mean, you just take the how do I call it, the derivative of this guy right over here, and so it would be a lot easier just to do the derivative of this versus having to do, well, really, you could have done it both ways. So scratch what I just said in the past like 2 seconds. So I continue forward as u is equal to t, and now I start to do my, I set my dv equal to e to the negative 0.08t. So I know my derivative of t, which is just 1 of dt. Now I got to do my integral to find my v. So I have 1 over 0.08 times e to the negative 0.08t. Now we got to follow up with this with the integrating by parts equation, which is u, well, the way I remember is ultraviolet voodoo, which is u times v minus the integral of v du. And so I have it over here. We start plugging and playing. So we have u, which is t, times v, which we found right over here, 1 over 0.08 times e to the negative 0.08t, minus our integral, right over here, of v times d du. So we have our v, which was right over here, times dt. Or we'll actually, and then from there, multiply by 1.1. Basically, this is just going to be a constant. So the constant follow along from right over here to this integral, all the way following down. Then I start simplifying down, as you can see from I have t, my multiply t right into this, right over here into this quantity. And so I eventually get t over 0.08 times e, which is to the negative 0.08 t, minus 1 over 0.08 times the integral of e to the negative 0.08. Now, if we look back, you're wondering, what in the world, how did I get this out of here? Well, I can see again, this is just strictly a constant. So like I did following my same logic as I did right over here in this integral over here, where I factored out the 1.1, I can also factor out the 1 over 0.08 following this math logic right over here. So giving me this quantity right over here is minus 1.1 over 0.08 times the integral of e to the negative 0.08 t times dt. And again, the 1.1 follows along being a constant. So now that I have this, I actually multiply my constant right through it. So I have the following equation as 1.1t over 0.08 times e to the negative 0.08 t minus 1.1 over 0.08 times negative 1 over 0.08 times e to the negative 0.08 times c, since we integrated. Whew, that's a mouthful. So now I just simplified this down strictly to this quantity right over here, which 1.1 over 0.08 times negative 1 over 0.08 equates to positive 171.875 times our e to the negative e 0.08 t plus our c. Now we got to continue with our math due to the fact that our next side is now we have to really think about, well, now we did all this integration. What was our goal, essentially? Well, we're still trying to find that mathematical differential, or from using that differential equation, we got to find our solution. So without getting too lost, we have to use this quantity right over here and plug it right back into where we found it, which is right over here in our y of t, which is going to be on the next page right over here. So now that we have y of t is equal to 1 over e to the power of negative 0.08 t times that whole quantity that we just solved for. So the best way to really solve this is really just distribute absolutely everything. Some portions start canceling out, such as this r e to the negative 0.08 t cancels out with this one, cancels out with that one, and follows through with our constant, which gives us our final solution as y of t is equal to 13.75 t plus 171.875 plus our constant, whatever it may be, times e to the 0.08 t. Okay. Now, we are done with part A. Now we got to continue on to part B. Our part B is asking, well, exactly how minimum does the bee population have to be before it goes to complete extinction? Like, basically, what is our threshold, our minimum threshold, before bad stuff starts happening and our bee population starts dying off? So the way I tackled this question was, well, we have our solution, which is boxed above, right over here, and I would just rewrote right on the bottom. And I asked myself, like, well, how am I gonna find my initial population? Well, I can really, essentially, at time 0 is our initial population without any growth, any death, or anything at all. So I can plug in 0 for time, really. So I can essentially say, well, y0 is equal to y sub 0. So right over here, I can basically say, okay, then, well, let's plug in 0 for t. Plug in 0 for t, following through. I find out my y of 0, which I have over here, set to equal to each other, is equal to 0 plus 171.875 plus c. Well, okay, then. Now we can essentially subtract our, how do I call it, to solve for c. We need to find our constant, really. So we can plug right back into the solution. We can subtract out 171.875 and find our c. So we end up finding that our c is equal to y sub 0 minus 171.875. Now, I took the c and plugged it right back into this above equation. Now I ask myself, like, okay, well, what does this mean? Well, the whole entire thing is that I eventually realized is like, well, what's this quantity essentially meaning? Because this two portions right over here, they're just linear. And right over here, this quantity, y sub 0 minus 171.875 times e to the 0.08t. This quantity, I'm going to call this quantity A as linear, and this quantity B as exponential. Well, I thought to myself, at 0, if y sub 0 equals to 0, then we're going to get a negative population. So essentially, no matter how high or no matter how great this quantity is, if y sub 0 is substantially less than 0, it's going to end up being too great of a negative to really start to have this linear function A have any effect on exponential function B. So once this becomes below 0, basically, or below, excuse me, not below 0, but below our 171.875, then it's essentially going to be this exponential equation is going to be too negative to where if no matter how great this linear function A is, there's basically going to be no point that the exponential function is going to take over and our B's will pretty much drive into extinction. So we can say that our basic minimum population in millions, if I recall, is going to have to be y sub 0 has to be greater than or equal to 171.875 million B's. Due to the fact is that if our B population does become lower than this quantity as 171.875 million B's, then all the B's are going to eventually drive into extinction. Thank you for watching. This is Francisco. Enjoy the rest of your